Yes. Next up is Nathan, who Robert Alberon will also get to introduce.
Okay, great. And so I was very lucky this summer to work with two amazing students. This second student, Nathan Xia, just graduated from high school and is taking off to the University of Minnesota in Twin Cities. He also has a deep interest in engineering and science and mathematics and space plasma physics. So this summer we were working with MMS data, and he did an electron flux analysis with the MMS satellites during the recent Gannon Day storm. Well, I guess not so recent anymore. It was May of 2024, but it was the largest geomagnetic storm in 30 years. So take it away, Nathan.
Let me share my slides real quick. Hello, my name is Nathan, and today I will present my project, Electron Flux Analysis from MMS during the Gannon storm. So, what are geomagnetic storms? So, geomagnetic storms are disturbances in Earth's magnetosphere caused by solar wind and coronal mass ejection, or CMEs for short. This can impact satellite operation and communication systems. Now, the Gannon storm is one of the most significant geomagnetic storms, like the most powerful in the last 20 or so years. It's driven by multiple CMEs, resulting in auroral displays and potential disruptions. The picture you see at the top is actually from the Gande storm. This picture is taken in northern mainland US, so it's pretty deep how far the storm reached. So the MMS mission, or Magnetosphere multi-scale mission, is NASA's fourth spacecraft mission launched to a high elliptical orbit, 70,000 to 159,000 kilometers in 2015, designed to study Earth's magnetosphere reconnection in dayside magnetopause and the nightside magnetotail. Also instrument for data analysis. So, so for MMS, so, so I'm using MMS spacecraft to simulate the storm dynamics during the May 2024 event. So the MMS data, so use a so we got high resolution measurements of plasma density, bulk velocity, temperature, pressure, and energy flux from the MMS-3 spacecraft. Now, I got the data from NASA CW Web and MMS, and I got the data. I'm using the MMS instrument called Fast Plasma Investigation, or FPI. Now, now I measured specifically from May 9th to 13th, 2024, as well as a few days before that. So I plot the omnidirectional energy spectra or flux distribution to study particle dynamics. I also examine temperature, pressure, and heat flux tensors in FPI flame, but I mainly looked at the the flux and visualize density and bulk velocity as well. So the goal is to compile an observational data set of the Gigante storm. So that was May 10th, 11, 2024, and using the telemetry data to capture temporal energetic variations. So like so the hypothesis is, so I believe a KP indices, which is the storm, which the KP indices, I'm sorry, which is how intense the storm has a direct correlation to to the plasma density, and MS, and also MS data will reveal distinct energy flux and velocity patterns during the peak of the storm. So what I did is I got the MMS-3 FPI and magnetic ephemeris coordinates, or MEC for short, which are like the telemetry of space, to analyze plasma, temperature, and pressure at orbits. So I also used NASA's Donkey API for KP index to find the storm's intensity. And then after grabbing the data, I created a visualization of the magnetosphere response. So the plot you see on the right is actually a series of storms between April 1st and July 1st, 2024. The bar shows the duration, and the scatter plots shows the intent KP index, which is the intensity of the storm. So I again I got the data from NASA's CWA Web for the MMS spacecraft and NASA's Donkey AVI for KP index, and to create the visualizations, I use Python libraries, cdflib to deal CDF files, pandas for data handling, matplotlib for plotting, and NumPy for numerical operations. So I first downloaded the MMS FPI data and later the MEC data for orbital position velocity, and I refined the visualizations and plots, and then I fetched the data from NASA's API to plot the storm intensity and durations. So here are the results. So these three plots so are the energy ranges and flux values before, during, and after the storm. So what I found is before the storm, the flux averaged between 10 to the 6 and 10 to 7 flux units, as you can see. I apologize if you can see it, but these plots are a little bit detailed, but they're it's pretty large. Um, and also during the storm, um, there's a very distinct separation of energy ranges, which as you can see, the highest energy range between like 10,000 30,000 have a lower flux values than compared to the lower energy ranges, which are somewhere between 6 and 80 eV. And after the storm is another distinct pattern. There are more inconsistency, and while also the for each energy range the flux values are more consistent. Another another Here we have the average energy ranges, and which are just grouped together, and the fluxes are averaged. So based on the previous three plots, there are 32 energy ranges, but now I grouped them, so each group has 8 energy ranges. So this visualizes better. So as you can see before the storm, like the lowest energy ranges are super consistent, have the narrow flux values, while anything between 50 and all the way to 30,000 EV has a wider range. And for during the storm, as you can see, between 6 and like 400 EV, there's a higher flux value, and and for higher energy ranges, there's a lower flux value, and this can be said for also after the storm as well. But the ranges are a lot narrower. Now these three plots are the distributions of the energy ranges relative to the flux. So this is how much activity, like also again, this is before, during, after the storm. What I found is that so before the storm, so so the so the the highest energy ranges had to have more activity at lower fluxes, and the lower energy ranges have more activity in the higher flux ranges. This is a very similar pattern for both before, during, and after the storm, but there are some discrepancies. Like, for example, during the storm, oh sorry, there are some like energy ranges between 500 and 800 or there are like at very high fluxes, and also like what I found is that like for there are generally higher activities, like regardless of flux, but like there are more activities for energy ranges for the lowest and the highest possible energy ranges, and in between there are less activity going on. And this can be said for after the storm as well. But but the lowest and but this time the lowest energy range has the most activity, and surprisingly, like the highest energy range had the least amount of activity. Basic, I forgot to mention these are stacked together. So for each flux value, the energy range adds up to each other. So you can see like which flux had the most activity as well as for each energy range as well. Now
Nathan,
these
Nathan,
we're
plot.
it's
at
past
9
9. Oh,
minutes.
yeah, go ahead.
Yeah, I'm sorry. I'm okay. So yeah, yeah. So for electron density, which is the concentration of electrons before the storm, it averaged around 2 per cubic centimeters, and during the storm, it peaked around 30 to 40 per cubic centimeter, and after storm, it's also went down to 1 or 2 cubic centimeter, but the graph is uh it's it's less consistent. This probably indicates some, I believe, like post-storm activities. And also for before the storm, you can see the sharp increase, and it likely suggests like increased solar activities or the storm is or like the start of the storm.
Why don't you move on to your conclusion slide? Thank you.
Yeah. So, so for conclusion, the pre-storm flux average around a lower EV and then surged to a higher EV during peak hours, and so this supports the hypothesis that increased flux have a direct correlation to the higher KP values. I also found that pre-storm energy ranges has shown like a narrower flux and expanding to, sorry about that, and during the storm, then and aligning the basically there's a correlation patterns as predicted by the hypothesis. And for electron density, rose sharply like at May 8th at this period of time, and stabilized. And there's a there's a increased density at high K intensity. And and for future work, I hope to integrate. I hope to like use real-time data to improve the accuracy as well. I apologize if I went over, but you I know I threw a lot at you guys, but you can read these key papers about the storm, and I also got the data sources here where I got data sources from. And also, lastly, I would like to thank Dr. Albron for guiding me through this project, N3 team, Ariana, Sam, Wendy, and Lynn for accepting this internship. I also like to give a thank you to Dr. Shape and Mr. Thornton. They're my high school teachers. They wrote the letters of recommendation. Yeah, that's it. Thank you.
All right. Amazing work. Thank you, Nathan.
I think that this storm had a lot of really amazing data that went with it.
Yeah, yeah,
That's
it is a pretty tough concept to understand. Yeah, I started a little bit. I apologize for that, but yeah,
But yeah, it's just amazing work. So good job.